Um, so first of all, I would really, really like to thank the organizers for having me here this week, because the IOA always feels like home a bit, and seeing all these dear faces around is almost overwhelming, so I'm kind of emotional right now. But anyway, I've decided for this talk actually to present something that saw its light right here in this room about 8.5 ago. There was a conference organized by Roberto and his collaborators, and we started discussing about this. And somehow it builds up on the work that I did ages ago, geological ages ago, I would say, as a PhD student right here. So somehow this little work, I think it belongs somehow to the IOA, so I'm really happy to present it here. So what I'll be talking about is the evolution of the clustering of, or environmental properties, if you prefer, of passive galaxies from the highest redshift we can probe at the moment down to the local universe. And basically, just to give you a little spoiler, what this no evolution in the environmental properties can suggest for what concerns galaxy formation evolution scenarios. So that was to move right. Oh, Jesus, it vibrates. All right, so what was the idea? You've seen already plenty of very nice JWST images and results. And something that I was talk about when I saw it is like amongst all the other things that you already seen, JWST is finding more than expected early type galaxies or creation galaxies, call it whatever you want, at redshifts as high as 5, but even redshift 7. And for those that are not, let's say, familiar with more extragalactic studies, redshift 5 implies 10% of the age of our universe, so like really, really early. And this is, I nicked it from a paper by Adam, recent paper of Adam. These are like sources. The sources basically I'm talking about. This is a different field, but still. These sources you can see are spectroscopically confirmed, quiescent, and they have like very high masses, stellar masses, between 10 to the 10.5 and 10 to the 11 solar masses, okay? There's a number of works that study these objects. The list is by no means exhaustive, but still, they've also been studied with KEK, that was the point. So we know they exist, we know they're more than normal than what we're expecting, but at that point, the question that we might want to ask is like, what are their environmental properties? And so we try to do this. It's strange that the title disappeared everywhere, but whatever, there used to be a title up there every night, but it doesn't matter. So JWST is great, but it's still not at the stage of having large enough, or I would say uniform enough coverage area to perform these large-scale structure studies. So for the time being, basically, we're relying on a homogeneous population of photometrically selected, robust candidate passive galaxies, selected in the work by Emiliano Merlin et al., 2019, in GUTS North and GUTS South, between redshift 3 and redshift 5. So these are our sources, GUTS South, GUTS North. You can already see by eye that distribution, this is doing something weird. I can really point here. You see that they really don't look already by eye randomly distributed. You see, especially in GUTS South, you can see a filament, you can see a pair here, you can see another pair here, and whatever. So our aim is basically to quantify this seemingly non-random distribution. And that's what we did. I won't get into the details. It's basically this plot is telling you, this is really weird, now it's just a T appearing, whatever. Whatever. So basically, this is just telling you the degree of clustering, so how much these sources basically talk to each other, or like, are more than randomly distributed. A random distribution would just be a straight line, zero level for W theta all along your degrees, okay, your distances. So they're definitely not randomly distributed, and actually their clustering, as I say, increases for a decrease in angle, which is expected for like galaxy formation and large-scale structure studies. Now, is this plausible? And again, I stole this plot from this paper by Adam, and these are different fields, right? So this is Good South, this is UDS, if I'm not wrong, but still they find one, two, spectroscopically confirmed and a robust photometric detection of passive galaxies within one proper megaparsec, which at redshift 4.6, it's about this point, okay? So it seems to be plausible. Also, I found this very recent paper here. It's very hard to pronounce, Nana Yakara, I guess, where actually they use this observed proximity of some of the sources to optimize their observing strategy. Okay, so let's say we believe it. Once we believe it, what can we do with this result? So to the zeroth order, you can fit this data just with one parameter, and this one parameter is basically the minimum mass of a dark matter halo that is capable to host at least one of such early type galaxies. And that's the point that you see here that we put here. Larger error bar is for just clustering measurements, smaller error bar if you also include information about their number density. Okay, the value that we found is about 10 to the 13th solar masses. And what I decided to do next is to put it into some kind of a context. So using basically all the results that I could find in the literature for passive galaxies selected in different ways. So this is, for instance, spectroscopic. It's actually to the F, George, still helps. Oh, Jesus, okay. And these are like, all right. And so basically the important thing is like there's a remarkable consistency, okay, of galaxies, passive galaxies selected in many different ways. And so what is this telling us? It doesn't seem to be any evolution in the dark matter content, and therefore in the environments, if you want, of the host of passive galaxies in the last 12.5 giga years. And if you find this like intriguing, I find this plot I'm going to show you now, that's basically my last plot, like even more striking. So again, this is the very same plot that I showed you before, with this very nice consistency, halo masses larger than 10 to the 13 solar masses, passive galaxies. However, you move to self-forming galaxies, and this is what you get. So the self-forming galaxies here, the only rationale was that they were selected with the self-forming rates larger than 20 solar masses per year, and these are like taken from like literature throughout the years, selected in any possible way. And you see that instead, in this case, you do see a very important downsizing effect. So actually, the straight line that's the best fit to the data evolves logarithmically as the redshift. So more in detail, what you have is like a high redshift, larger than redshift 2. You have that basically this self-forming activity happens in protocluster-like structures, so very massive halos, while locally you find the same amount of self-forming activity in much smaller structures comparable to our Milky Way. And you see that the passive galaxies, so in this case, increased evolution, in this case like flatness, and passive galaxies, so the y-axis are the same, it will kind of like nicely wedge in here. So that's my very last slide. So what does this imply for galaxy formation or growth scenarios? So I think that with these results, we have two scenarios open, at least that I can think of. The first one is that early type galaxies are just fully formed and already in place at redshift 5, 7, or whatever, probably going to find more. And their evolution just proceeds in a totally passive way. They don't form stars any longer, except for maybe some bursts, little bursts. And also the environmental properties remain the same. So the conclusion of this scenario is that basically these objects, the objects that you observe locally are exactly the very same objects that were formed at redshift 5, a very high redshift. The second one that I kind of like better instead envisages a very strong connection between these very early high redshift, early type galaxies and star-forming galaxies at later redshifts. So basically, if you see here, the scenario would be that you have these objects that then slightly later, they become basically the seeds for faster creation of like gas and more galaxies, and eventually end up as the central galaxies of clusters locally. And so the conclusion of this scenario is that these objects, the early type galaxies that we see now, are definitely not the same that we see a high redshift, since these high redshift ones would have been converted later into much larger, much bigger galaxies, and hosted in much bigger dark matter halos, having become cluster-centric galaxies. And there is some evidence that I think supports that. First of all, is the number density of local clusters and these high redshift passive galaxies, that basically the same. And also the fact that these star-forming galaxies that we find at redshift 3, not only they're hosted in very massive dark matter halos, but also have like large stellar mass content, evolved stellar mass content, or the order of 10 to the 11, 10 to the 11.5 stellar masses. And I think it's hard to achieve such a high level if you don't have already a seed, a massive seed to accrete that. And I think I'll stop here, sorry. If you have more thoughts, just ask me questions or tell me. Thank you.
Thank you, Manuela.